All right, we are back for more torsion. Last time we looked at the beginning lesson on torsion. Just torsional shear stress is all we really did. We did limit our torsion to circular shafts, so rods and tubes. We did that just to, that's normally the kind of shaft that is under a torsion type of load. It doesn't have to be. You could have a hexagonal or triangular or square or any other shape cross section, but what would change is in our equation, the denominator, the polar moment of inertia, would be based on whatever cross section you did have, and we limited that to circular cross sections. So we worked through a couple of problems on torsional shear stress and torque in the different sections of a shaft. And today we're going to add on to that the idea of angle of twist. So one way things could fail is they have too much torsional shear stress and they exceed whatever your limit is. Maybe you have your limit set up for yielding stress, not to exceed some number. Now these are shear stresses, so the yielding shear stress, or maybe a fracture strength or something like that. But it could be that the shaft just twists too much, and that's considered failure. So today, that's what we're going to look at. We're actually going to continue looking at the torsional shear stresses, but we'll add on the idea of angle of twist. And so just looking at the remaining schedule here, we've got today with angle of twist. Then we've got kind of a wrap up on torsion, and we're going to add in this idea of power transmission. A lot of times that's what an engineer is doing with one of these shafts, is they're transmitting power someplace from an engine to a transmission or whatever it might be. But there's usually some shafts involved in power transmission, and usually those shafts have a circular cross section. Not all the time, but usually. And so we'll do that Monday. Wednesday, we'll do a one-shot topic, thin-walled pressure vessels. And then Thursday, we will do a one-shot stress concentration factors, and we're done. We're done with new content anyway. Then you've got the following Monday is if you want to redo exam 1 or 2, we'll have time slots for that. And again, just like we've done the other exams, a noon and a 7 o'clock. And then exam 3, which is going to cover these new topics: torsion, stress concentrations, thin-walled pressure vessels, plus sections on all the stuff we've done back at the beginning to now. Then we do have the lab report, or well, not the lab report, the project report. Don't forget that you need to do the project report. It's a decently, let's see, what percentage did we make that? We made that 10%, so it's a letter grade. So the design project 10%, that is that trust project simulation group project thing. Your homework is web work, you know what that is. We've got those two lab 1 and lab 2. Those were SolidWorks simulations, 2.5 points each. Moodle quizzes, there were 5 of those. We haven't done the 5th one yet, but there are 5 of those, and they're 2% each. And then the exams. And so we're getting really close to being done. Let's talk first about our angle of twist. So we need to, I think we defined all the variables last time except for angle of twist itself. So we'll kind of redo some of that, and then we'll talk about angle of twist. So let's draw our shaft. I don't know, something like this. And then let's make a copy of that thing. Can't find my cursor. There it is. Something there. And let's do that. And maybe that. Oh, well, that's good enough. Let's erase this one because it looks very strange. There's our shaft. Maybe we can, skew it a little bit to make it a little more like that. All right, and so we applied, this could be hollow or a solid one. It doesn't really matter. It does change the denominator, but we did that last time. So actually, let's not apply the torque yet. So we're talking about angle of twist. And it would probably help to also, while I've got this going, draw an end view of the cross section. So like that. This is the circle of the cross section. So let's define a couple of points. Let's use blue, and let's put point A right. Well, I need to put it maybe here. So that could be a point right here. And then let's draw a line, like as if this were a real shaft. Let's draw a line down the outside surface. What would that be? Like that. So this will be line AA. Got endpoint A on one end and endpoint A on the other end. Now let's apply our torque. So let's say I apply a torque like this. If I apply a torque here, then the other end has to have the reaction torque. We'll just put it over here. You know, the other end could be attached to a motor or whatever, but the other end has the opposing torque on it. So if I apply enough torque, then let's imagine the left side of this shaft not moving. So it's like it's bolted to the wall or whatever, and I'm applying this torque and I'm twisting the shaft. So if I do that, then let's use a green line, and this will be point A prime, which on our cross section here would maybe look like that. And the angle of twist, how much I twisted it, you know, the green line is the blue line, but after I've twisted it, it's kind of rotated around some amount. So the angle of twist would be this angle. So angle of twist is theta, and it would be how far did I twist it? Saw a question. Will there be some guidance of how to go about simulating designing our truss? Yes, there will be. I guess I didn't put that on the little schedule of things we're going to talk about, but I'll go through. You can do it however you want to, but I will go through one method for using SolidWorks to simulate a truss, because SolidWorks does have some truss element, like in the finite element suite of things. There are some truss elements, and there are some ways that might be easy for you to use if you want to go down that path of simulation, or we can you can just draw the thing like you normally would and load it as a static simulation, and it'll give you similar results, but they won't be the same as truss assumptions, but it'll be okay. So I will go through that. Probably would Monday, probably Monday we'll have, because most of Monday is one new topic. Today's also a short day, but Monday I think would be a good day to go through the how you can simulate a truss. So yeah, there will be. All right. So that's all angle of twist is how far did you twist the shaft measured from one location to another location. So in here, I've got from the left end of the shaft to the right end of the shaft, and there might be reasons why you have different distances, and we'll look at some example problems. One thing about angle of twist is that it is going to, whoa, I thought we had turned that off, but apparently not. Hold on. Got to do my resetting of the screen, or it's going to go crazy on us. I actually thought I had just checked that, but something I did re-upped it, I guess. I don't know. There we go. All right, now let's get back to where we were. Something like that, I guess. Maybe we weren't quite that large. What I was saying is, when you calculate angle of twist from our equation, we'll look at the equation in a second, it is going to come out in radians. Okay, so that's just the way, most equations, theoretical equations, work. is because, you know, that you can have equations that generate degrees. That's is a thing, but degrees are kind of made up. You know, we could have chosen there are 400 degrees in a circle, but we chose 360 degrees in a circle for a variety of reasons. One of them being that 360 is evenly divisible by a whole bunch of numbers. You know, so it makes it dividing up easy to do. But we could have chosen some other number of degrees in a circle, but radians actually have a real meaning. So here's our little aside for why most of these equations come out in radians. So here's our circle, and here's our radius r. So the definition of a radian is that I take the radius and I map that length to the circumference of the circle, and whatever angle that makes, well, let's not use theta because we don't want to confuse it with our other one. Let's use alpha. That is the definition of 1 radian. So this distance here, this arc length, equals r, the radius, and whatever angle that is created by basically swinging your radius through one length of radius on the circumference, that's how a radian, a single radian, is defined. So it actually has a meaning related to the circle versus degrees, which are just the number we chose to divide the circle into. Where 360 doesn't really mean anything, we defined it to mean that, where radian actually has a definition based on the circle itself. So most equations that you're going to deal with, unless they have some, you know, factor in them somewhere or coefficient or something, they're going to give you radians as your answer. You could have, you know, we could build in a conversion factor into our equation that takes the radians and outputs degrees. So you can have equations that give you degrees, but they're probably going to have, or they have to have, some kind of conversion factor from radians over to degrees. So angle of twist in your equation is going to come out in radians. So how we calculate this is theta, so that's the angle of twist, equals, and it's very similar here to the delta equation. Delta equals, remember, delta equals a change in length equals P times L over, actually I think we used F. Sometimes use P, sometimes use F. I think in this one we used F because then it spells flea. So I think we used FL over EA. The angle of twist equation is a very similar equation. So instead of force, though, we have a torque. It is still dependent on the length. So the length being, in this case, the length of the rod. E is the modulus of elasticity, and it talks about, you know, it's the slope of our linear elastic region when we do a tensile test on a piece of material. You know, it's that slope. There's a similar material property called modulus of rigidity. And it's basically the same thing as E, except instead of doing a tensile test to figure out E, we did a torsion test. And so we will put G in here. And then A was our cross section, because the stretching was a force that was perpendicular to that cross section, or compressing it, either way. Here it's not A. What we've been using for the cross sectional property for torsion is J. Remember, J is the polar moment of inertia. And it equals the integral of rho squared dA, where rho is the distance from the center outwards along a radial line. But we have limited our conversations to circular shafts, and so we have the definition of pi over 2 times c to the fourth minus b to the fourth, where c is the outer radius, b is the inner radius, or if you want to deal with diameters, pi over 32 outer diameter to the fourth minus inner diameter to the fourth. So we are limiting ourselves to these, but these are only circular cross sections, circular shafts. Okay, so our equation's pretty straightforward. Just this little guy. So that's not too difficult for us to deal with. I was trying to center that. There we go, more like that. So let's just grab some problems to work on and see if we can apply this. And probably these problems are also going to ask us about torsional shear stress. G, there was a question, how do you know G? G is right beside E in our material properties chart. So we might as well go ahead and get one of those up. So let's see, where do I have them? Here, material properties, here. So if we look right next to, well, that's really small, but let's try a little larger. Modulus of elasticity here. The very next column is modulus of rigidity, which is G. You might even want to label E for elasticity and G for rigidity. It does have a G in it, but it's not R. R is a different thing. So it's in the charts. Okay. Let's see. I picked out this problem last time. So last class time we were doing some of these problems, and I looked at this one and I thought it would be a good one for today. So why don't we do this one? We can do more than this one, but let's start with this one. All right. We've got our electric motor. It's supplying some amount of torque, 5.4 kilonewton meters. Here's a little, whoops, whoa, got it. I don't know why I did that. Constant diameter, cold rolled bronze. So line shaft. You don't have to know what line shaft. That just means that these there's multiple gears all lined up on the shaft there. Constant diameter. So what that means is that anywhere this shaft, it doesn't change diameter. So that's not always true. There are plenty of stepped shafts where they get gradually, they're thicker in the middle and they get gradually thinner, not tapered, but they step down. That's very much a thing. But that would kind of complicate the problem unnecessarily for what we're trying to do. So this one's a constant diameter shaft, and that'll help us make this problem flow a little easier. And they give us the material, cold rolled bronze, so that's where we can go to our material charts over here. What unit system were we in? We were in metric, so let's go to our metric chart. So where's metric? There's the metric one. Cold rolled, here's cold rolled bronze. It looks like 45 is our number. Those units are gigapascals. So G, let's go ahead and cold rolled bronze. G, I think it said 45 gigapascals. Just for a reminder, 45 times 10 to the 9th for gigapascals. You would not normally have a cold rolled bronze shaft. I think this problem is just set up that way so that you go find some other material versus just the regular stuff. So you might have a cold rolled bronze shaft. It's probably not not in this application, I wouldn't think, but in this one we do. 3 machines are driven by gears B, C, and D. So B, C, and D, we don't know what they are, but somehow machine B is driven by this larger gear, C is driven by this middle gear, and whatever machine D is driven by the last gear. What we do know is the amount of torque that each of those machines use to do whatever their job is. And so we have that. So we have to determine the minimum shaft diameter required if the maximum shear stress is limited to 100 megapascals. So basically we know the upper limit, or we know our allowable shear stress is 100 megapascals. So one of these sections of the shaft is going to have the highest stress, and that's the one that drives the diameter size for the whole thing, because it's a constant diameter shaft. So we don't have to go find individual diameters for each section. We just find the worst case section and design for that one. And that's relatively common too. It makes it simpler, to deal with. Sometimes you need to have the shaft step down and each section have its own diameter, but there might be reasons where it's just a simpler thing to just design for the worst case and let the others be over designed. So the other part of the problem is the angle of twist of D relative to A. So basically how much the entire shaft twist is. We want to calculate that. What is that angle of twist? In degrees, though. It does say in degrees here, so we will have to convert it. All right, let's do part A. So part A is like last time's content. I think what we'll do is, why don't we draw us a little free body diagram of the shaft, I suppose, and work from there. So something like that. And into the input, again, we don't know, is it going clockwise or counterclockwise out of the motor, so let's just pick one direction and we'll work with that. So let's say that that's our input direction, and it says 5.4 kilonewton meters is how much is input. And then at B, some of that is removed by machine B. For me, machine B was, these are, so B, C, and D, so 2.6 kilonewton meters. There's more of the input removed at C, which is 1.2. And then finally, D with 1.6. Now, hopefully, our input, let's just check, our input 5.4 should equal all the output. So 5.4 minus 2.6 minus 1.2 minus 1.6 does indeed equal 0. So all that we put in comes out somewhere. How do you know when to switch direction? So on this problem, I picked one direction for the input because the problem doesn't tell me. The problem here, in all of its description, it doesn't tell me which way is this motor spinning. So I don't know that. So I have to pick one direction. And it's okay with torsion, or well, with shear. Shear stresses, they don't care if I'm going one way or the other. For most all materials, there's probably some unique materials where it matters which way you shear it. But for all the materials that you're going to engineer with, for things like this, it doesn't matter which way the shear happens, so you just pick one direction in the absence of knowledge of which way it actually is going. So that's the 5.4. I picked one direction for it. And the problem does tell me, let's see, how does it say it? Right here. They tell me that 3 machines, we don't know what the machines are, but 3 machines are driven by gears B, C, and D, and they require these amounts of torque. So when I get to B, C, and D, those are not adding to the torque in the shaft. They're not helping the motor, right? The motor is powering them, and so they're removing some amount of torque. And I've got those values: 2.6, 1.2, 1.6. And so if I were to make any of these 3 arrows the same direction as the input direction, they would actually be helping the motor to do its work. And so these are kind of the outputs, and this one is the input from the motor. And so I don't know which ways they're turning because the problem doesn't tell me. I just know that whichever way the motor's turning, the outputs are the opposite of that. So that's how I know when to switch. I don't know which direction necessarily. It's just the opposite of whatever the input is. If I drew any of these 3 the other directions, then they would be helping the motor versus the motor powering them. So that's kind of a way to think about it. Let's see. All right, so this does add to 0. So if I do the summation of torques here, they need to add to 0 because the shaft is spinning, right? But it's delivering all of its torque somewhere. What we are doing is we're ignoring that, this bearing and this bearing and this bearing and even that bearing. They're real in the real world. They're absorbing a little bit of this input torque because they're not perfectly frictionless, but they're close enough to frictionless that we're just saying that, well, whatever amount these little bearings absorb is negligible. So we are ignoring that, and that's true for this problem. Now, if you get maybe your mechanical engineering and you get all the way to the end, then yeah, we do have to start worrying about what kind of power absorption are these bearings dealing with, because it is real, it's just small. But that's not for this course. So if I add up all these torques, and let's just say I give the 5.4 a plus sign, then I would be writing 5.4 kilonewton meters, and then if I gave the 5.4 a plus direction, then these other three are the opposite, so they're minus. And so that does indeed add to 0. So it's kind of like true. All right. The problem, though, wants me to calculate how big do I need to make this, I colored it pink, this pink shaft, in order to limit the shear stress, the torsional shear stress in that shaft to 100 megapascals. Okay. So we could do several different things here. Let me see what the labels are. So let's say that this is point A, there's B, C, and D. So one of these sections has the highest amount of torque. Now, if you think about it, it's pretty obvious which section has the highest amount of torque. But if you're not sure, or you just you can't convince yourself that no, that should be that way, and you want proof that it's that way, then what you do is you look inside each section. So you open up section AB there, and sure enough, you draw your little free body diagram for AB, and it has that input torque of 5.4 kilonewton meters, and inside there then has to be 5.4 kilonewton meters. So equals the torque in section AB. So that's going to be the highest amount of torque. But if you're not convinced of that, then you do have to take some more time and all right, well, let's check section BC. So you cut open BC, draw that free body diagram, and it's something like this. And I've got the input 5.4. I've got the gear at B removing 2.6 kilonewton meters, or sending it off to somewhere. It's sending that 2.6 kilonewton meters, it's sending it off to machine B. So it's kind of like a budget. I've got 5.4 available. I'm going to send 2.6 of it to B. Some people get confused. Well, how does it know how much to send to B? It doesn't. It just, B consumes that much of it. It needs that much torque in order to operate. And you might do that through some gear ratios or whatever. Maybe it's based on the power from the whatever B is consuming power-wise. So it's just a budget of this is the available part, and this percentage gets sent to B based on the way I've designed the system. We just don't know what B, C, and D actually are. We just know how much torque they're consuming. This course, actually the next, like on Monday, we'll get a little hint of how B, C, and D get sorted out. But this course is more concerned with, well, what's the, if I know that, then what's the stress in these sections or the angle of twist. So here it looks like I would need internally, in order for this to balance, I've got 5.4 and then I've got minus 2.6. So I need another 2.8 kilonewton meters inside here in order to make that free body diagram in equilibrium. So that would be the torque in section BC, which is smaller than the torque in AB. And then if you want to make absolute certain, you cut open the last section, CD, and draw that free body diagram. And you've got your 5.4 going in. You've got the 2.6 going off to machine B. And you've got the 1.2 going off to machine C. And that means you need another 1.6 in order for this free body diagram to be in equilibrium as far as the torques go. And that would be the torque in section CD. So then, of these three, of here, here, and here, the problem wants me to design the shaft based on the worst case one of these, so it is AB. Are all of exam 2 grades released? I think you can see them, but I haven't gone in and corrected everything. So yes, but not. I think maybe you mean, are they their final form? They're not their final form right now. But you should be able to see them. I don't know. Maybe if you can't see them at all, then let me know. It means that Canvas has them locked down for some reason. But they haven't been like finally gone through. All right, so AB, torque in AB is our worst case torque. And so now we go and solve our shear stress equation. So from last time, that was tau equals T times rho over J. But when we want to deal with maximums, like the worst case, then we've got tau max equals T times C over J, where C is the outer radius. And in this problem, they told us the maximum allowable. So they said that we cannot have maximum shear stress any more than 100 megapascals. So they actually gave us tau max. And the worst case torque is the 5.4 kilonewton meters. We don't know C. C's the outer radius, so that's just C. And then it doesn't say anything about inner radius or tube or hollow. So does it actually say anything about it being... Doesn't say really. It says line shaft, but it doesn't give us any reason to think that this is a hollow tube. So we're going to assume it's a solid rod type of shaft, which not all, but many shafts are solid. So we're going to use pi over 2 times c to the 4th. So all we have to do is solve this equation for c. So it looks like I've got a c there, and that can go c cubed. Let's get my calculator out. 100 megapascals, pi over 2. And then let's take our 5,400 newton meters and divide by the coefficient that's with the c cubed. And then let's take the cube root of that number. So let's raise that to the 1/3 power. And that's going to be a radius, and this probably is asking me for diameter. So let's multiply times 2. Millimeter. And a couple of little like internet breakups there. Hopefully it's staying working. It looks like it's streaming right. All right. It might skip, but it's been pretty like skipping half a second. So we'll see. So that C, well, no, actually that's not C. That's D. C is half of that because C is a radius. And I multiplied times 2 to get a diameter. Okay, so that's similar to what we did last time, except this time we're solved for D versus solved for the stress. So the okay, so I don't know why it's acting so flaky today, but we're almost done. Usually if it's a hollow tube and we're asking you a question about that, it's probably related to the wall thickness. You know, how thick does the wall need to be, and we give you the outer radius, or vice versa. You know, maybe we give you the inner radius. It has to go over a shaft, and you need to figure out how thick the wall needs to be. Oh. Come on. There we go. So there's our tube. So if you are working, this is not for this problem. If you are working on one where you want to do wall thickness, and you've got, you know, the inner radius as B, outer radius as C, then the wall thickness, that's easy enough. Wall thickness equals C minus B. So that's not a big deal. What usually happens on those problems, though, is that you're dealing with diameters. And so remember that if you're doing diameters, then the wall thickness is not equal to the outer diameter minus the inner diameter, because that is actually 2 wall thicknesses. So you need to divide by 2. So if you do run across a problem with asking about wall thickness, and you're given diameters, just remember that the wall thickness is outer radius minus inner radius, or outer diameter minus inner diameter, all of that divided by 2. All right, so that's because it's not hollow. All right, so let's do the other part of this. The other part says find, or determine the angle of twist of D. So and the coupling are at 2.4 millimeter intervals from each other. So, and they tell us a different diameter for our shaft. And same material though, so cold rolled bronze. So the interval thing, what they mean there is that this distance is whatever, that's the interval. And it told me that it was 2.4 meters. And same for this. Remember, we need that because the angle of twist equation has length in it. And so these are going to be the lengths that the equation needs. Okay. And then they give us the material property based on that cold rolled bronze material property. Okay, so this problem is going to work a lot like the axial deformation, where we had a bunch of different loads applied and each section could either stretch or compress. That's the same thing that's going to happen here. It is possible we could arrange a problem. Let me look at web work real quick. Well, not that, that's 4 horsepower. Here, we could arrange a problem where one section is going one way and the other section is twisting the other way, and so they have to subtract from one another. This problem, each section has the same sense of torque. In fact, we've already done that right here. So the internal torques for each section are all in the same direction. So all of these angles of twist are going to add together. That doesn't have to happen. We can, you know, contrive a problem where the one section is twisting clockwise and another section is twisting counterclockwise, but we've already determined on this one that all of the internal torques are the same direction. Okay, so this problem is just going to be a matter of calculating each of those angles of twist. So Um, angle of twist for section AB. Remember, our generic angle of twist equation is theta equals TL over JG. Although I think I wrote it GJ. Doesn't matter. It's multiplication, so it doesn't matter what order I write it in. So angle of twist for section AB is T for section AB, 5.4 kilonewton meters. And we could go back up here. That's just this value right here. The length, actually the length for all of the sections, they're all, section AB is this first one from A to B, and they're all 2.4 meters. So this will be 2.4 meters. And they all have the same material, and they all have the same polar moment of inertia. So the denominator for all of these equations is going to be the same. The only thing that's going to change is T. So L, J, and G are the same for all of these. In fact, we could go and figure out what L over JG is, and that could just be multiplied times all these different T's. I'm going to write it out, though, in long form so that we don't miss any steps. Let's do pi over 2 times, they gave me a diameter, I believe. Yes, they gave me 73.5 millimeter diameter, so C is a radius. 70, what was it? 73.5. That's millimeters, though. So I do need to be sure that I'm working with the same types of units. I have meters in the numerator, millimeters to the fourth in the denominator, so I'm going to convert them all to meters, I think. Although, it's fine. We'll do meters. So that means that I need to take this conversion factor. All right, so let's see. Or I could do the conversion before I do the raising to the fourth power, whichever way I want to do it. Maybe I'll do it that way. That might be simpler. Okay, I think, we'll check and see, but I think L over J times G is 83764.8392. That doesn't seem right, actually. That actually doesn't seem to be right. Let me check that again. Let's see. 73.5. Well, so 0.0735 would be the meter version of that, divided by 2, raised to the fourth, times pi over 2, and then 2.4. That's a super tiny number. 2.4 divided by that answer gives me that large number, but then I need to multiply time. That's, what am I missing? Something. TL over JG, those are meters. Torque is kilonewton meters. It is solid, so pi over 2 times c to the fourth. Because that's going to give me way more radians than I would need. So what am I doing wrong? Oh, I might have a, I might know. Let's see. Pi. Whoops. Oh, I might be hitting the wrong button for one thing. Pi over 2. Okay, that's that. Then divide by 0.0 735 over 2 raised to the 4th. Oh, I didn't put G in there. That's the problem. Let's fix that. I wrote down some numbers, but I never wrote G. There's more to this equation. So all of that times G, which is, what was it? It was a big number, 45 gigapascals. So yeah, that's why we're so far off. 45 times 10 to the 9th pascals. Okay, so if I divide this by 45 10 to the 9th, then I get a 0.10107 radians. So that's why it was coming out to be like billions of radians, and that just didn't make any sense. But I didn't divide by the modulus of rigidity. All right, theta from B to C, everything's exactly the same except the internal torque for BC is 2.8 kilonewton meters. So 2.8 kilonewton meters, same length because it said all the intervals were the same 2.4 meters, and same cross section, same material. I'll write this one differently just to show a different way to write it. And so what I would expect is to get a smaller amount of radial twist. But let's find out. Whoops. It does help if I put the right numbers into the equation though. Okay, and I get, this is about half, 2.8 is close to half of 5.4, and I do get about half of the amount of twist. And then the final section from C to D, everything's the same except I've got 1.6 kilonewton meters, so about half of what I just calculated. Okay, let's see, 1600 times 2.4 divided by pi over 2 divided by 45 billion, and I get 0.03061 radians. And these, I gave them all the same sign because they all have all of their torques. So here, here, and here are all in the same direction. Here, oh, that's, well, I can't do that. Covers it up too much. All of their torques are in the same direction, so they get the same sign. And the total angle of twist from C, from D. From D to A or A to D, whichever way you want to do it, is equal to the individual ones from A to B plus B to C plus C to D. And 0.10107 radians plus 0.053563 radians. I'm having to carry lots of decimals because they're such small numbers. Plus 0.03061 radians equals, let's see, 0.10107 plus 0.053563 plus 0.03061, 0.18523 radians, If I want to know degrees, I multiply times 180 degrees per pi, and I get times 180 divided by pi, 10.614 degrees. And then we check in web work. 10.614. Show the correct answers. Oh, all right. So, and even with my keeping up with a lot of decimals, I didn't store them in my calculator, and so it wants 10.45 because every one of these is rounded. You know, I rounded every one of those values, and then I added the rounded values and rounded that, so just too much rounding. So for web work purposes, you really have to store the values in your calculator in order to make it happy on these kind of calculations. This one is exact, 180 over pi, that's exact, but this was rounded based on these three, which those three were each rounded, and it just didn't work out. So I'm not too concerned that we got 10.6 and it wanted 10.5, so I think that's fine. Web work doesn't think it's fine, but I think it's fine. So I could have stored more values. Okay, let's see. Oh, I rounded the diameter? Whoops. I might have. 73.5. Oh, I did. That's probably what it is. I didn't mean to do that, and I didn't round the right way. But it is. It's probably there. Oh, because I converted it. It's not 0.5 anymore. I converted it over, and I just dropped the 5 for some reason. So, there you go. That's why it's off. Got to be super picky with all of these for web work to like what you're doing. I did it right the first time. Oh, I actually converted it a different way the first time. All right. So that's kind of angle twist. That's could we make it more difficult? Yes, we could have a hollow tube that's twisting in multiple directions, and so some of them you have to have as positive signs, some as negative signs. So we could make it more complex, but only in the sense that the math gets more tedious. The concept is actually really, you know, there's not a whole lot to the equation, other than remembering that G is a material property, modulus of rigidity, not modulus of elasticity. And other than that, and doing all your conversions and multiplication correctly is probably the harder part. So there's not a lot to these. You have, let's see, this is the optional. You know, remember the optional 3 or optional sets of homework are just for practice. I did open SA03, which gives you 4 problems that can be for bonus. These are the harder problems. I haven't even looked at what they are. Actually, that's a there's one that's a torsion type thing. So just have more going on. That one doesn't look like it does, but there's more. There's a hollow and a solid and a rotating disc and all that kind of stuff. There's a torque. This one's interesting because it kind of shows you how the torque might be generated. Here's one where you've got a lever arm with a force on it, and that's showing you how you might generate some torque in this tube. There are different ways. We aren't really concerned with how you're generating the torque. You know, we've been using these motors where inside the motor, you know, there's electromagnets and electric fields that are creating the torque that is wanting to twist the shaft. So we're not really too concerned with how the torque gets generated yet, but that we know what the torque is. All right. So I think that's a good stopping point. These topics are not lengthy. Monday will probably be a little bit longer because I do want to show how to do the SolidWorks stuff, but the content, the actual content for the course is pretty simple, the power transmission stuff. And we'll do a work through some problems. On your team, on your group project team, there's plenty you can go ahead and do. I still haven't found a working version of MD Solids. Let me just check and see if it's still not letting you download anything. Yeah, same thing as before, where it doesn't want to download that. So I haven't found a way. Maybe it's just not working anymore. But there are other similar things that you can use, online truss simulations, to get a bunch of ideas, because part of the project is identifying whatever it is you want to build or design a truss for, and then generating several ideas for that. I expect at least one idea per group member, and then picking through one of them based on whatever, why, explaining why you didn't want to use one of these other designs and you went with this design, and then simulating. So there's plenty of stuff you can do without the simulation. If you don't know how to do the SolidWorks simulation, that can be later on. There's plenty of things you can do leading up to that before Monday. For Lab 2, you can run through the list and explain it. The list. I can. I'm just not sure what the list is. For Lab 2, could you run through the list? Maybe the... Let me look and see what list is on here. Lab 2 is talking about a 3-point bend test. So that's what... and it's a simulation again. So let's see what might be in here. Lab 2. Lab 2 guide with points. Maybe we can look at that. That's a list. If this is not what you're talking about, then let me know. But I assume this is what you mean, because this is the rubric of what goes in Lab 2. So first thing is just a title page. That's pretty straightforward. Second thing here is the objective. So you might have to do a little bit of background research on what a 3-point bend test tells you. Now, what we're doing is for the memo. Okay, so that's probably this. What we're doing is a simulation. We're not actually doing a real 3-point bend test. But if you were doing a real 3-point bend test, you had your little planks and you had your fixtures and you were taking data, then what were you hope to gain by doing a 3-point bend test? That's what this point is talking about. Methodology. This is how did you set up, maybe not like button click by button click of how you set up the simulation, but okay, but the general idea, you created a so many inch by so many inch by so many inch plank, and you loaded it in this way. You put a whatever pound point load here. You did these kind of supports, that kind of information on the methodology. The results is, so this is assuming you have SolidWorks working. Now, if you're one of the people who just hasn't been able to get SolidWorks working, then you'll have to grab this from the stuff that I've done online, and so you'll just have to kind of, you won't have access to as many results as somebody who actually can run the simulation on their computer. So your results section, assuming you can run SolidWorks, would be a graph of load versus displacement. You could calculate flexural strength. So you could get flexural strength and modulus of elasticity, all these things. And you don't have to include all of these, but those are things you could include. So one of the things that you're often trying to do with the 3-point bend test is get a modulus of elasticity value, because you've got a beam, basically, that exactly matches one of your beam deflection setups, where it's simply supported with a point load in the middle of it. And so if you know how far down it deflected, then in the real world, how far down it deflected, then you can take your equation that gives you the maximum deflection, and the only unknown value in that equation would be E. And so you can solve that beam deflection equation for E and figure out your modulus of elasticity. That could be one way to calculate modulus of elasticity. Obviously, you can get modulus of elasticity from a tensile test specimen. That's maybe the more traditional way, but that's one thing you could do. Or maybe you just want to have a load versus displacement graph or whatever. Again, if you don't have the simulation in front of you, then you've just got to take a screenshot basically of the stresses, because I think that's all I showed was the different stresses of the 3-point bend test, and comment on that. So I'm not, basically whatever you do, grab. It's not saying you need to have this and this and this. It says it could include those things. So whatever results are available to you, pick some of them and write that up. These memos are not meant to be long. They're meant to be pretty straightforward. Then you discuss, all right, based on what results you do show, maybe it's the stress analysis, you pick out something to talk about that. And then if you had any references, if you grab stuff from the YouTube video, that's a reference. There's probably not any appendices in this one, but if you have any, then you can put those in here. One result is fine. One result is fine, because that's all that some people might have. If they can't run SolidWorks, then all they've got is the one plot, or image of the stress distribution. I think that's all I showed. Maybe I did the displacement one, but I don't actually think I even did that. So just one result is fine in here, because this is really a technical memo, so it's a short thing. The report for the project, the class project, the group project, that's a longer thing, like 10-ish pages or so. This is 1 or 2 pages, so this is not a long thing. It's really just to get people familiar with doing the simulations. You would not actually do a 3-point bend simulation or a tensile test simulation in SolidWorks. You would do some other kind of simulation, but so this is more just getting familiar with SolidWorks. So it's not crucial that you have every one of these things that it says here in results. I can't highlight just results. You don't need all those. You just need one type of result. So the header, so it's a memo format. So this is actually at the top of the first page. So it's going to look like, let's see. It's going to look like this kind of thing. Right there, where that's the header, and then your write-up is right underneath that. And you probably have 2 pages. So that's what it is. All right, so anything else before we close down? I'll wait a second to make sure that we're caught up on the chat. All right, looks like we're caught up on the chat. If you have questions, oh wait, all right, there we go. If you have any, put them in Discord, it's in the email, whatever. Power transmission, which is also a torsion type of problem, and a simulation in SolidWorks or an example in SolidWorks of how you can simulate a truss in SolidWorks. So that'll be next time on Monday. We include all the relevant pictures. So I'm thinking 1 or 2 pictures, maybe 1. So some of it will be if you can show the fixturing, like how you supported it in your simulation, and then a results picture. That would be plenty of pictures. So I'm thinking the thing is 2 pages, maybe 3 pages, but only if you use really large pictures. All right, so we'll be back Monday with some torsion and some SolidWorks.